The following video is based on topics learned in previous lessons. If you're just starting out with Bitcoin, you may want to review some of our more basic videos before moving forward. What is SegWit? Will it truly allow for Bitcoin to scale for mass adoption? And how does it even work? Well, stick around. In this episode of Crypto Whiteboard Tuesday, we'll answer these questions and more. Hi, I'm Nate Martin from 99bitcoins.com, and welcome to Crypto Whiteboard Tuesday, where we take complex cryptocurrency topics, break them down, and translate them into plain English. Before we begin, don't forget to subscribe to the channel and click the bell so you'll immediately get notified when a new video comes out. Today's topic is Segregated Witness, or SegWit for short. SegWit is an upgrade to the Bitcoin network that was activated in August of 2017. It was first introduced by developer Peter Vela at the Scaling Bitcoin conference in December of 2015. SegWit aims to solve several issues, one of which is Bitcoin's scalability. Bitcoin transactions are written on a blockchain, an immutable ledger on which transactions are bundled together into blocks that are chained one to the other in order to determine their order. A new block is created roughly every 10 minutes. Additionally, Bitcoin's protocol limits the capacity of a block to 1 megabyte, which limits a Bitcoin block to around 2,700 transactions on average. Well, this creates a problem when a lot of people are trying to send Bitcoin simultaneously, as the queue of transactions waiting to enter the blockchain gets longer and longer. While Visa can process 1,700 transactions per second, Bitcoin can process only 4, not nearly a scale that could handle mass adoption. In order for Bitcoin to truly become usable on a worldwide scale, it needs to find a way to increase its transaction capacity. Another issue SegWit addresses is transaction malleability. Every Bitcoin transaction has 3 parts: who sent it, also known as input, who receives it, output, and a digital signature that verifies that the sender is eligible to send the coins. It turns out that Bitcoin's code allows digital signatures to be altered while a transaction is still waiting to get confirmed. The signature alteration can be done in such a way that if you run a mathematical check on it, it's still valid according to the network. But if you run a hashing algorithm on it, it gives a different result. Let me explain with an example. For the sake of simplicity, let's say that the signature value was 3. But instead of 3, I change it to 03, or 3 plus 7 minus 7. While mathematically the values are all the same, so it's still a valid signature, if I hash the different versions, I'll get different results, since hashing depends on how you write the value and not just the value itself. Since the hash is the transaction's ID in the blockchain, this means I can effectively change any unconfirmed transaction's ID to a different ID and it will still be valid. Creating a new transaction ID for an existing transaction can be problematic for a number of reasons. First, if you want to build second-layer solutions on top of the Bitcoin network, like the Lightning Network, you need to make sure no one can alter the first layer since the one relies on the other. If you want to learn more about the Lightning Network, make sure to catch our episode about it as well. Second, altering transaction IDs can cause issues if you're spending or accepting unconfirmed funds. Let's go through another example. Alice pays Bob in transaction X, which is currently unconfirmed. Bob uses these unconfirmed funds to pay for a product online from Charlie, transaction Y. Meanwhile, Charlie sends Bob his product before waiting for confirmation on transaction Y. Well, after receiving his product, Bob does some technical tinkering and maliciously changes or malleates Alice's payment so that her transaction X gets confirmed but with a different transaction ID. Transaction Y, which is what Bob sent to Charlie, is now invalid since it relies on transaction X's original transaction ID that now no longer exists. So Charlie won't get paid, even though he's already delivered the goods to Bob. Bad Bob. While scalability and malleability are the 2 most burning issues that SegWit addresses, there are a variety of other technical issues that SegWit tackles that don't necessarily affect the end user directly. Now that you know what SegWit is, let's talk a bit about how it actually works. Segregated witness is a proposed change to how blocks are structured. Non-SegWit blocks, also known as legacy blocks, have a total of 1 megabyte of space for all of the block data: inputs, outputs, signatures, and additional scripts. SegWit blocks, on the other hand, are in fact large 4 megabyte blocks that consist of a base transaction block and an extended block. So, contrary to popular opinion, SegWit is indeed a block size increase. SegWit blocks move the digital signature and other data known as the witness outside of the base transaction block. The witness data will still be transmitted, but it's placed inside the extended block. So the base transaction block includes the information about the sender and the receiver, and the witness data is left blank and doesn't take up any more space. This allows for more transactions to fit inside the 1 megabyte base transaction block. The extended block, the additional 3 megabytes, include all of the witness data that isn't mandatory in the base transaction block. The new block format SegWit introduces achieves two major goals. First, it moves the digital signature outside of the base transaction block. This way, if someone changes the signature on the transaction, it won't affect the transaction ID. This, in effect, solves the transaction malleability issue. You know, Bob. Second, it shrinks down the base transaction data. Since the witness data takes up to 65% of the transaction size, moving it outside of the base transaction block allows more transactions to fit inside that 1 megabyte block. Now, I know what you're probably thinking. If SegWit is in fact a block size increase, why not just increase the block size to 4 megabytes in the first place? Why all of this hassle and block size debate if the end result is in fact bigger blocks? The answer is really quite simple. Developers wanted to avoid a contentious hard fork in the Bitcoin network. You see, Bitcoin's protocol specifically states that blocks can't exceed 1 megabyte. So developers had to find a solution that will allow the network to accept both SegWit and non-SegWit blocks if a hard fork were to be avoided. The solution of a 1 megabyte block with an extension of another 3 megabytes is something that is still acceptable under the existing protocol. Legacy nodes receive only the 1 megabyte base transaction block without the extended block. They still consider them valid. SegWit nodes receive both the base and extended block, up to 4 megabytes in total, and can validate the transactions in full. This backwards compatibility is also known as a soft fork. This approach is a lot less risky since it doesn't require nodes to update their software to support SegWit. It means that even if it takes years for all of the nodes to upgrade, the network will still function.
Now let's move on to how SegWit blocks are measured by miners. While legacy blocks are measured in size, SegWit blocks are measured in weight. Block weight is a new concept introduced in SegWit, and it's calculated on a per-transaction basis. Each transaction has a weight, which is defined this way. The size of your base transaction, meaning that which doesn't include the witness data, times 3, plus the full transaction size, and that equals your transaction weight. Legacy transactions don't have the ability to strip away the witness data from the base transaction, so their weight will always be 4 times the transaction size. For example, a legacy transaction of 1,000 bytes will have a weight of 1,000 times 3 plus 1,000 equaling 4,000.
SegWit transactions, on the other hand, are going to have a weight of less than 4 times the transaction size. For example, a 1,200 byte SegWit transaction comprised of 400 bytes of witness data will have a weight of 1,200, the total transaction size, minus 400, the size of the witness data, leaving the base transaction size of 800. Times 3, making 2,400. Add the total transaction size of 1,200, and that equals your total weight of 3,600. In short, the larger the size of the witness data, the lighter the transaction weight will be. This incentivizes miners to prefer lighter SegWit transactions over heavier ones, since they can fit more of them into a base transaction block, which increases the potential miner's fee should that block be accepted and confirmed. While in theory, SegWit transactions can create a block of up to 4 megabytes in size, in practice, the average block size that includes SegWit transactions is around 2 megabytes. Today, almost 50% of all Bitcoin transactions are SegWit transactions. Since legacy transactions are larger in size, they require higher network fees to get confirmed faster. And finally, SegWit addresses start with a 3, while legacy addresses start with a 1. Thanks to its advantages, more and more popular wallets and exchanges support SegWit. Ledger, Trezor, Electrum, Exodus, and Coinomi are just some of the major wallet brands that have already adopted SegWit. It's important to note that if you have a legacy wallet and you want to move to a SegWit wallet, you'll need to create a brand new SegWit wallet and move all of your funds to its address. There's just no way to upgrade your existing legacy wallet to work with SegWit. SegWit is the first of many upgrades that will gradually allow for Bitcoin to scale for mass adoption. It's a fundamental change that will allow further developments down the road, like the Lightning Network, Schnorr signatures, and more. As more and more wallets adopt SegWit, it will soon become the standard for any Bitcoin transaction. Well, that's it for today's episode of Crypto Whiteboard Tuesday. Hopefully by now you understand what SegWit is, an upgrade to the Bitcoin protocol that segregates the witness data from the base transaction data, hence achieving a smaller transaction size, securing transactions from malleability issues, and more. You may still have some questions. If so, just leave them in the comment section below. And if you're watching this video on YouTube and enjoy what you've seen, don't forget to hit the like button. Then make sure to subscribe to the channel and click that bell so you'll be notified as soon as we post new episodes. Thanks for watching me here at the whiteboard. For 99bitcoins.com, I'm Nate Martin, and I'll see you in a bit. The witness data from the base transaction data. Data. Developers wanted to avoid a contentious. Yes. Legacy nodes receive only the 1 megabyte. 1 megabyte is now invalid since int. I'll get there.